Actually, before I get started talking to about some of that stuff, just kind of following along with a bit of the economic analysis we were doing a few minutes ago. I don't know how many of you guys know about this site called the Privacy Rights Clearinghouse. They track data breaches. They started in January of 2005. And I gave a talk one time where I just sort of like expounded on this for a while. And at the end of their list, it'll tell you the number of total records breached, right? And it's an ongoing list. So it's up to something like 400 million now. A guy named Larry Ponemon, runs Ponemon Institute, did a report where he studied how much does it cost to recover from an attack. And he said that the average cost, based on his research with organizations, was $202 per record to recover from an attack. So when I see stuff like that, I like to do math. So the slide is a bit old. It's over 400 million breached records now. But if you just take it at the time I built the slide, multiply it together, I mean, so a year ago, from 2005, $51 billion has been lost from attacks, and it makes me ask questions like that. And so then I start thinking, gee, what could we have done? Well, we could have bought 393 million barrels of oil, could have sent 2 million people to the University of Washington last year. Here's one that kind of hits home for some people, saved the lives of 82,000 people. I like this one especially. If we just built secure systems and we didn't get hacked, then we could feed 4.5 million or 5.4 million families every year. Anyway, I just thought I'd kind of show that. I thought it was interesting since we were talking a little bit about some of the economics of attacks. Who am I? I'm from Amazon Web Services. I have kind of the enviable or maybe unenviable position of becoming the guy who goes and talks publicly about AWS security. So some people think that's really cool. Some of my colleagues think that's really cool. Our PR department is completely scared to death of everything that comes out of my mouth. But we are looking at ways we can be more transparent, because we absolutely realize that the only way we're going to continue to win business is by addressing the elephant in the room, which is how do you protect data on an infrastructure that you don't own? So I'm going to go through pretty quickly here, because I actually did think of a few questions that I want to ruminate on with you guys together near the end of the talk. Because I've got some ideas about some things I want to do next, and I'd like to help you guys, or I'd like you guys to help me prioritize that. And if you have any questions or comments as I'm kind of going through some of the material, that's okay. Just please let me know. So am I not filling the room enough? All right. So, are you recording it? Oh, okay. All right. Turn it on. Okay, so now this is posterity, so I really have to be careful what I'm saying. One of the things that Hoff talked about in the beginning was resiliency and redundancy being kind of important. And so, yeah, we do view that as a critical element of being secure. And to help you build applications that can be resilient, we've got data centers and facilities in 4 areas of the world for compute and storage, and 16 areas of the world for content distribution. I think probably what gets a little bit more interesting is what happens in some of those facilities. So we break down a geographic region into language we use. We call this an availability zone. Now, it isn't exactly the same as a single building, but that's sort of how I've depicted it on the picture here. Most regions have 2 availability zones. On U.S. East, on the East Coast in Virginia, we've got 4 availability zones. What do you get with an availability zone? Well, as much as we can, we try to keep them separated geographically. You don't want to flood bringing down all 4 of your data centers, so we separate them when we can. Or earthquake. A little difficult in Singapore, for example, because it's one tiny little island. It is one single floodplain. It is one geographically area. But we do what we can, right? Now, I'm going to get into this a little bit later. Depending on the particular way you're storing data, we're going to make multiple copies of that for you. So again, this is this idea of sort of built-in resiliency. And that might be moved between availability zones within a region. The important thing to understand is that we will never move data automatically from one geographic region to another. Because we understand that in many instances, you might be bound by regulatory requirements that say data that goes in Europe has to stay in Europe. So if you put it in the data center in Ireland, you can be confident that it's going to stay in Ireland. It will not, on its own, move to Northern California. Now, you're free to move it if you want to. You can. We're not going to stop you from doing that, but we don't do any region moving automatically. Yeah?
Is that defined by data site or by political zone? In other words, is it the data site, this data site in Ireland or Ireland?
So, yeah, you say this is Republican data and this is Democratic data. Is that what you mean? No, it's... No, yeah, you say what we do is give you the region. So EU West is the region, right? Or US West or US East or APAC. Now, if you want to start an instance, not only do you pick the region, but you also pick the availability zone. You want that instance to go in as well. Good. There. All right. We don't actually draw attention to them. You know, there's one instance where security by obscurity actually makes sense, and we think that's in where the facilities are. And so, you know, when we construct something like this, we actually don't put an Amazon sign on it. There's pretty high degree of physical security that's required to get into the buildings. You get, you know, I'm not allowed, even though, I mean, my job is to communicate about AWS security to people because I don't have a role that requires getting physical access to the facilities. I actually can't get in there. I don't have any permissions to do that. Only our operators can. Everything is logged, probably on that ancient dot matrix printer right there, too, I think. Now, let's talk a little bit about what happens with the services and the data movement. So with S3, which is, just think of it as like, you know, persistent disk in the cloud, simple DB, which is a simple flat file database, and multi-AZ RDS. So RDS is a relational database service that we released several months ago. Instead of starting an instance and then installing MySQL on it, RDS is a pre-configured MySQL for you. You can get that now in multi-AZs. When you store an object, so let's say it's a Windows machine and you X-copy something onto, you know, like a D drive that's well, no, say you put it in S3. D drive would be EBS, sorry. So you put it in S3. We will make multiple copies of that, and we will put that in multiple availability zones automatically. That's just part of the feature. We make a distinction between service level agreement and durability. So the service level agreement for S3 is 99.999%. The durability is 11 nines. We have recently announced something called the reduced redundancy storage for Amazon S3. So instead of 11 nines, I think it's, is it 9 nines for reduced redundancy? Yep, okay. Too many numbers. I mean, I used to work for Microsoft, right? Going from a company that releases a new product every 7 years to a new company that releases a new product every 7 days is a mental challenge to memorize all this stuff. But the idea is, even with the reduced redundancy, you still get those multiple copies. It just isn't as many copies as you get. EBS, I need to define probably what EBS is first. So when you start an instance, you get some disk that goes with the instance. That disk is for the operating system. That disk is not durable. Right? So there's this whole notion of servers are disposable horsepower. They come and go. Don't worry about debugging things. Just terminate and restart. What matters a lot more now is the data and what you do to protect that data. So if you're going to build a database server, you want to go grab some disk somewhere. That's what Elastic Block Store is all about. And then you attach that to your instance. In that case, because that is disk that's attached to a virtual machine, and virtual machines live in only one availability zone, an EBS volume lives in only one availability zone, but we still will make multiple copies of that information for you. And you know, you write something, and a half an hour later, you want to read the thing you wrote back. And if your read request happens to land on a drive that died at that very moment, we will detect that that drive failure happened, and we'll just send you off to another one of those copies and give you that back. We don't even give you an error message, but our operators will know that, you know, drive 7 in frame 5 in building 4 died, and so they'll go in and replace that drive. So what does that mean when that drive dies? I'll get to that in a minute. So on EC2, the compute cloud, the disk that's there, we call that ephemeral storage. And we don't want you to rely on that for anything. I'll tell you a quick story. One of the things that helped me learn a little bit about some of these details on how some of this disk stuff works, we had a customer who had a SQL server that was, the database was on the instance store. It wasn't on an EBS volume. And read our recommendation and said, you know, that's really not the way to do that because it's not durable. He said, yeah, okay, I better replicate that stuff off. So he fired up a replication job, which is going to take a little bit of while, or a little bit of time. So he went home that evening. His boss logs into the management console from home, sees this another instance running that's replicating data, and says, I don't know what that is, and hits the terminate button on both of them. Now, then they call us, and they want us to restore his data. Well, we can't really do that for you. Let me tell you why. When you allocate an EBS volume, we go, logically it looks like a volume to you, right? But really what we do is we go find unused disk space, assemble that together into a volume upon which you can put a file system. But before it shows up as available in the console for you, we are zeroing out those blocks. So there's a little bit of delay there, right? So you get nice, fresh, clean physical blocks as well, and then you put your file system on top of it. But for all of the rest of the services, what we do is rely on the virtualization layer where we create a logical to physical block mapping, right? So that whenever you get disk, if there's data that's already on the disk, you can't read it because we mark that data as being owned by somebody else. So since it's not your data, even though there might be something on the, the physical magnetic surface there, the logical mapping table prevents you from reading that. And so here's an interesting thing that I learned in this experience with this guy with the SQL server. If you were to get into one of our data centers, physically get into the data center and actually yank a disk out of the thing, you're not going to be able to make any sense out of the data that's on there. It's a collection of bits from a variety of customers. There's no context that makes sense to you as an analyst of the data that's there. So it's just essentially a bunch of scrambled bits at the physical layer. It only makes sense at the customer layer, at the layer that you can see. So that's how disk is handled. Now, what do we do with CPU? Yeah.
Is that just more of a property of how you strike, or is that a security property?
Yeah, that's kind of an interesting question.
Strike in the broad sense.
It's more of it's a mechanism that we keep in place to make sure that the hardware is as maximally utilized as possible, right? So just by making sure that we keep that hardware in use and that it doesn't sit there idle. But it also allows us to spread the data out across multiple pieces of hardware. So if you've got a 300 meg file, it's actually quicker to read that thing back because it might be coming from 18 physical drives all at once, right? Even though it looks like a single volume to you. It's just part of the architecture. And then you get a security benefit out of that, right? Because only we know what's happening at the physical layer, and that's not exposed at the logical layer. And even at the physical layer, our operators can't make sense out of that data because it's lacking the context.
So would it be fair to say, using something like a Linux file system as comparison,
Yeah.
all the metadata that you would normally see in IO tables is stored somewhere else. You're just allocating big blocks.
Right. Yeah. I mean, at our level, at the physical level, we can't even make a distinction between a GIF image and the inodes that would go with that, right? We don't see that. Is there another question? Yeah.
Just extending on that, so this could be done randomly just to optimize for space and reuse it or optimize for probability of exploitation. Is there an optimization of one of the?
Not really. No. It's Yep. Yeah.